Alright, this is gonna be a fun video. This is where I explain the dark magic. Yeah, so this is gonna be a video about the group theory behind VR and like how I motivate this method. Uh, you're really not expected to understand this unless you know group theory. So if you don't know group theory, feel free to skip this. But if you're one of the theory maxers, then yeah, just keep watching the video. So let's start with the group of that acts on the E-slice edges, and this is just S4. The edges are completely free to move around, but also their orientation is locked, so it's just S4. Yeah. Good old S4. And the thing that I did is that I looked at its normal subgroups, and let's just list normal subgroups. It's the trivial subgroup S4. That's A4. This doesn't yield anything good actually, because there's already parity restrictions in the cube, and so basically this turns out to be useless. But that's B, which is the namesake of the method. This is the Fiat-Gruppe, also known as the Klein group. The Klein 4 group has similar names, I guess. And this consists of 4 elements, which are the trivial permutation, this swap, and this swap, where I'm imagining the 4 elements to be at the corners, I guess, of the square. Yeah, this is supposed to be a race. What am I doing? All right, and so this is a normal subgroup of S4, and the elements. This is a commutative subgroup, and also this is a vector space over F2 if you want, because under addition. This is quite easy to see because this is just Z2 times Z2. So yeah. And these properties make VR possible. Let's show how. So let's actually start by showing. Well, actually, before doing this, I actually also mention one other thing. S4 mod V is isomorphic to S3. Okay. This is something you should be knowing as well. And this is isomorphic to a 7-yard product. I don't think it's a huge deal if you don't understand this part here, but this is motivation. That's supposed to be a mod. What am I doing? Yeah, this is also something that's true. And this ZMod 3Z is the thing that appears in the arithmetic knot theory, basically. So yeah, let's start. Let's explain why my magic works. So we start with a skeleton, and so a skeleton. Well, we start from like the slice before even doing any moves. Okay, and this is some element in S4. And then we're doing some generators. So we're doing psi1. Actually, let's write them backwards. Psi minus 1. Sorry, psi minus 1. So psi1. And this is equal to, let's call this final permutation sigma. This is our final slice state. But actually, let's just assume that we already modded by V. Okay, so this actually, we can call this like, I can put the bar over the top just simplified. But let's just assume that these are, instead of, so it's kind of hard. I'm doing a terrible job explaining, but basically, I'm considering this equality in S4 mod V. Okay, these are all in S4 mod V. And also this lies in, well, A3 mod V, sorry, A4 mod V, which is just A3. Okay, because V is a subgroup of A4. And this is just something in S4 mod V. These are generators, so these are either R2, L2, F2, V2. Well, but because we're modding mod V, yeah, because we're quotieting mod V, then actually R2 and L2 are the same thing. Because R2 L2 is just a 2-2 swap on the edges, and F2 and V2 are the same thing because that's just a 2-2 swap on the edges. Also, E2 is in V, so E and E prime are the same thing, which is why VR really separates between the core slice insertions and the E2 slice insertions. Okay. Is there something else? Another thing is that R2 F2 R2 is the same thing as E modulo V. Not quite because it centers. So that's something that, yeah. I mean, that's a slight annoyance, I guess, but not really, because we're always doing center insertion, like e slice insertion in pairs. So yeah. All right. So let's actually um, write down some more definitions. So I'll call row F2 R2, and phi is R2 F2 R2, which is that here's F2 R2 F2. And I'm only concerned about the slice, which is why I'm allowing myself to write stuff like this. This is not about it if you consider the UND layers. Obviously, this is off by 2e2e outside of the slice. Now, one thing that you can notice is that F2 is equal to, well, let's see, this is equal to phi rho. And R2 is the same thing as phi rho inverse. Okay. Also, one thing that I want you to understand is that phi is rho inverse, which I like to say to mention this fact as phi anti-commuting with rho. Okay. Also notice that phi and rho are the flip and rotate generators of S3. If you think of S3 as being the dihedral group on the triangle, so it's just the flip and rotate, which you're probably familiar with. Right. And yeah, this is basically isomorphic. They satisfy the same rules. Another thing, one thing I'll mention is that my original formulation of VR that I did in January, actually, I did not use these generators and I did not use arithmetic mod 3. I just did calculations directly in S3 by noticing that R2 and F2 are Coxeter generators of S3. This is fine. It's more complicated than just doing arithmetic mod 3, though. Yeah. So that also requires like a lot of things like figuring out what this chi is. Notice how sigma is actually very easy to figure out what this is. This is just go to the end. Chi, well, it's technically not hard, but you need, like my original formulation, you need to do an all of R-ness to do, and so yeah, I'm doing a very poor job explaining stuff. Okay, so let's actually write down some relation between this psi and this sigma, okay, and whatever the hell we have remaining. So I'll just write psi I. I'll define this as being phi to 0 to the alpha I, and also sigma is going to be defined as rho. Actually, it's not a definition of sigma. It's a definition of what is on the right side. I'm just going to define this as being rho to the alpha. Remember, sigma is a new implementation because of parity restrictions. Okay. These parity restrictions are the reason why A4 doesn't really bring anything new, really. Okay. This doesn't look like a. Oh my gosh! Delete the wrong thing. I meant to kind of fix this psi. Okay. So now let's just write this equation in these terms. We get chi, and then we have phi rho to the alpha n, phi rho to the alpha n minus 1, phi rho to the alpha 1. And this is equal to rho to the alpha. Now remember that phi anti-commutes with rho, which means I can pull all these phi's to the left, basically to here. So we basically get chi times, we get phi to the n. This is phi, not rho. And then this is rho to what? To the sum from I going from 1 to n of minus 1 to the I plus 1 alpha I. And this is equal to rho alpha. And this is our first equation. Okay. Now, let's just say that we are able to insert phi's at some point, and these are, and in such a way that this sigma becomes the trivial permutation, well, it's mod b. Okay. So, yeah. So, for example, let's just consider. I'll just do it in case of one, like of two e slice insertions, which are next to each other. just because that's a bit simpler to work out. But as an exercise, you can do this in a more general case. Number of phi's are starting to be even because you need to preserve parity. So I just say cyan, and now here you have and I just call this sigma prime. Okay, and we assume that this is the identity actually. So let's assume this is the identity. Obviously, this isn't always possible, but yeah, we're just working the simplified assumption for now. Just because I just want to show you how the thing works without dying of notation. As an exercise for the viewer, do the general case. I really didn't use this exercise. What am I doing? All right. So let's just do our usual thing. So what happens at this spot? So this spot we get phi, and then remember psi I is phi times rho to the alpha I. So this is phi, and then rho to the alpha k, and then we have our other red phi. Now these two cancel, and what happens? What happens is that basically we have commuted phi past the rho for free. We commute one phi plus the rho for free, but without changing the sign, which means when we pull it back to the left, we do change the sign again. So basically what happens is that we get, this is the same thing as chi, and then phi to the n, and then rho to the sum, I going from 1 to n, of -1 to the I plus 1, times alpha prime I, where alpha prime I is defined as alpha I for I not equal to k, minus alpha I for I equal to k. And we're requiring this to be the Taylor permutation. Okay. Now, so these are our two equations. Okay. So let's actually compare these, and we notice how we got chi times rho to the n in common. So basically, we get a chi rho to the n, sorry, phi to the n, not rho. This is equal to both rho to the power of, well, from the first one we get alpha minus this thing, so alpha plus. And from the second equation we actually get all right, which means these two exponents have to be the same modulo 3, because remember this is the order of rho. So, and notice how this alpha is really our goal number. Okay? Alpha corresponds to our goal number because it's just the assessment of the final state, which is sigma. Okay, sigma is just like the final state that we get at the end after applying the skeleton. Okay, so we get modulo 3. Now we can cancel a lot of things here because remember most of the alpha i's are the same. So basically we get alpha plus alpha k congruent to minus alpha k modulo 3. And from here, we can subtract alpha k from both sides, and -2 is congruent to 1, which means alpha k is congruent to alpha modulo 3. So basically, we get that this insertion only works if we pick something that is equal to the goal number. If we were to put multiple pairs of insertions, notice how the things which are in the middle of the segments, so bounded by like an odd number of phi's on each side, they would change sign, and the things outside would not. And so the things that do change sign would not cancel out, and the other things would. So this is basically why the method works. Yeah. Also, actually, I lied. There is a -1 to the k here. Sorry. There's a -1 to the k. Actually, let's write like this. Yeah. notice also that, yeah, there's this -1 to the k appearing. So we do get the alternation of which it is. And notice that the difference between R2 and F2 is the axis. Remember that we thrown an information which is not the axis away already. So yeah, this is why there is this alternation of axis, which is equivalent to the RF thingy, if you think about it for a sec. So this is why step 1 works. Okay, so I don't think I've done a particularly good job at explaining it, but hopefully you see that it's actually like really easy. It's very simple concepts. Let's just quickly go through why step 2 works. Remember, in step 2 we're just inserting E2 moves. So how do we insert E2 moves? And yeah, how do we insert E2 moves? The way we insert E2 moves is so let's do a concrete example. Let's say we have something like this. Okay, this is our VR. Okay, maybe the volumes are all like here or whatever. Doesn't matter. And let's say we want to insert an E2 move here and E2 move here. So basically, we're assuming that the result here we're in the field group already. We have a 2E2E. Let's not worry about centers. The way centers work is very easy, obviously. Like it's just another Z2. So there's no need to worry about that. So yeah, what is the effect of inserting an E2 here and here? Well, to insert an E2 here and here, all you need to do is just multiply by the inverse of this, then multiply by E2, and then multiply by this again. So so inserting E2 here and here is the same thing as so we did one insertion, and then the next insertion is just sorry, this is supposed to be E2. What am I doing? All right. So notice how E2 is in the field group. Well, if we just look at the edges, and since so basically the field group is normal, so this is also in the field group, which means this is going to add to the final state using like the field group addition, basically. Also, how do we determine what this is? We just look at two opposite edges. So this is how insertions work. You look at what happens there. And how do we know that we can still use, that it doesn't matter what the state at the end is? This is because the field group is commutative. Also, you can look at all the 2e2e swaps and notice that the opposite edges are always G, basically. They're always they don't share colors in any case. So yeah, this is also how step 2 works. Very simple. There's also a way to predict step 2. It's not super worth it, but on paper, because you still need to figure out what the final slice state is. But the conjugation action of S4 on the field group factors through S3. This is just another way of saying that the field group is commutative. So it factors through the quotient. So basically, you can actually use just the numbers that we came up on step 1 to figure out what happens there. This is like complication because we widen moves, but that's actually kind of fine. Yeah. So yeah, this is the math behind the VR. This is how it works. This is the group theory. Very simple. Again, I think I explained quite poorly, but you should see that it's actually very, very, very easy. So I guess we'll see in the next video. I'm not quite sure what I'm gonna do in the next video yet.